When it rains over a catchment, part of the water will infiltrate in the ground, and part of it will flow as runoff and finally end in rivers. In this lesson, we will see how the hydrograph resulting from a given rainfall is formed. A hyetograph is a graphical representation of the rainfall intensity, here rainfall intensity over time, presented either as a continuous curve or, more often, as a histogram. A hydrograph, here, is a graph of flow past the point in a river as a function of time, and it can be directly related to the rainfall through a transfer function. To establish such a function, we first need to identify the different components of a hydrograph in order to keep only the part related to runoff that is caused by the net rain. To explain this, let us consider a long-duration rainfall with a constant intensity I0 over a time T0. At the beginning of the rain, all the water infiltrates in the ground. Then, infiltration reduces and the depression in the terrain are filled with water and the runoff progressively starts. The red line indicates the evolution in time of the runoff discharge. Then, when the rain stops, the runoff slows down, the superficial detention progressively disappears, partly by infiltration and partly as a delayed runoff to the catchment outlet, while the water stored in depressions infiltrates in the ground. The resulting runoff hydrograph is thus the red curve. Another representation of the fate of rainwater is the one illustrated here, where the different parts of the rain volume are detailed according to their destination. The hatched zone here covers the different forms of infiltration. The moisture refill, when the air present in the pores of dry soil is replaced by water. Then, the hypodermic flow or interflow, that is the flow just below the ground surface, that will reappear as runoff further downstream in the valley, for example at a change in ground slope. And the underground flow that supplies the river during dry periods through sources and resurgences. This constitutes the base flow of the rivers. So, the discharge in the river is constituted by four parts. The direct supply of water by the rain falling over water surfaces, for example on lakes. Then the runoff flowing during the rainfall event, the interflow with a short time delay, and the underground flow that supplies the base flow during dry periods. And finally, we see that the brown zone here represents a volume which pertains to both types. An infiltrated volume that will also contribute to the river discharge, but with some delay. These illustrations here summarize the fate of rainwater, comparing the situation before and after urban development. Before urban development, almost all the rainfall is taken up by plants, evaporates, or infiltrates through the ground, leaving less than 1% of surface runoff. After urban development, surface runoff increases significantly, while evaporation and infiltration into the ground decrease. As we have seen in the previous representations of the hydrographs, the discharge progressively increases when it starts raining. We will define Tc, the time of concentration of a catchment, as the time required for water to travel from the most hydraulically remote point in the basin to the outlet of the basin. So we see that before Tc, only part of the basin contributes to the discharge here at the outlet. And when T becomes larger than Tc, the whole basin contributes. The duration of the rain is TR. When T is between TC and TR, here, all the basin contributes to the discharge at the outlet. Then, when the rain stops, the flow continues at the outlet until the complete emptying of the basin. Remember that the most remote drop of water takes a time Tc to reach the outlet. So, until a time equal to Tr plus Tc, flow can be observed at the outlet. We will now analyze some factors that influence the shape of the hydrograph resulting from a given hyetograph. Let us consider the impervious semicircular basin illustrated here, that has a total time of concentration of 4 hours. We can divide this basin into 4 sub-basins, having each a time of concentration of 1 hour until their respective outlets, with the same area. As the basins are assumed to be impervious, there is no infiltration and only runoff is considered, without baseflow. Consider now a uniform rainfall of 10 mm per hour intensity during 1 hour, so a total volume of 10 mm. The resulting hydrograph over the subbasin A is this one, with a triangular shape. Indeed, the discharge increases until Tr equal Tc, that is until T equal 1 hour, then the rain stops and the discharge decreases until time Tr, 1 hour plus Tc, that is here 2 hours. We can do the same for subcatchment B, taking into account the fact that the water exiting this subcatchment takes 1 hour to cross subcatchment A before reaching the outlet. Then we have similar hydrograph for C and for D. When we add all the contributions from the 4 subcatchments, we find the final trapezoidal shape of the hydrograph. We can observe that the duration of the hydrograph is Tr, 1 hour, plus Tc, 4 hours, and this duration is called Tb, the base time of the hydrograph. Let's consider now a rainfall with the same total volume of 10 mm, but with a duration of 4 hours and an intensity of 2.5 mm per hour. The resulting hydrograph for subbasin A increases until Tr equal Tc of subbasin A, that is 1 hour. Then it remains constant until Tr, that is 4 hours. And then it decreases for 1 hour. Adding the contributions of the 3 other subcatchments in the same way yields the final resulting hydrograph with this triangular shape. If we compare the 2 cases, we see that again the time base Tb is the sum of the rain duration Tr and the time of concentration of the entire catchment Tc. Indeed, we have for the second case Tr equal 4 hours and Tc equal 4 hours, so a time base of 8 hours. We can also observe that the maximum discharge here is the same for the 2 cases that have the same volume of rain. Let us consider a third case where the total volume of rain is still the same, that is 10 mm over the whole catchment, but the distribution over each subcatchment is different, with a higher intensity over subcatchment A. We see that we still have the relation in the resulting hydrograph, the relation Tb equal Tr plus Tc. But now the peak discharge is directly influenced by the subcatchment that receives the largest intensity. Finally, if the temporal distribution of the same 10 mm rainfall changes, for example, a higher intensity over the first 20 minutes, then a lower one over the remaining 40 minutes, we can see that the hydrograph first increases with a slope corresponding to the higher intensity, then it continues increasing, but with a slope corresponding to the lower intensity. The final construction is done as in the previous cases, and we observe that we still have Tb equal Tr plus Tc. We also observe that the maximum discharge depends on the volume of rain and that the concavity of the hydrograph can be related to the time when the maximum intensity occurs. The analysis that we just performed is of course oversimplified for several aspects. However, it allows to identify one key relation, this one recalled here. The time base of the hydrograph is the sum of the time of concentration and of the rain duration. Let us now look more in details at the shape of an actual hydrograph. After a rainfall, illustrated here by the hyetograph here in blue, the discharge increases. The rising limb of the hydrograph is the concentration curve. The concavity of this curve is different from what we could deduce from the simplified analysis, because in the reality, the discharge increases more slowly at the beginning, as long as a significant part of the water infiltrates. We then have the peak discharge at the maximum of the curve and the falling limb when the discharge due to the direct runoff decreases. Finally, when the flow due to the rainfall has stopped, we have the Baseflow recession curve. The Baseflow recession can be considered as constant for a given basin, as its shape is almost independent from the rainfall. The part of the hydrograph below the dashed line here is the baseflow. That is the part of the hydrograph due to underground flow. This exists even when it does not rain. The part above the dashed line is the runoff hydrograph. That is the part directly due to the rain runoff, with a duration Tb. And this is what will be collected in the drainage system. So we need a method to separate the two parts of the total hydrograph. The starting point A of the runoff hydrograph can in general be easily identified, because from this point the discharge increases significantly. For the final point, there are different methods. The simplest one, but the less accurate, is just a horizontal line from A to find the point B, that is the end of the runoff hydrograph. Another method consists in considering that the falling limb lasts n days after the peak, resulting in point D here. The baseflow line is then either just a straight line between A and D, or an estimated curve through an estimated point C. Finally, a more accurate method consists in considering that the baseflow recession curve has a decreasing exponential shape, starting from a point Q0 that has to be determined on the basis of the following analysis. Indeed, the groundwater table behaves as a reservoir that is progressively emptying. Equation 1 expresses the volume of water released during time step dt. Equation 2 is the basic equation of groundwater flow, where the discharge is proportional to the head h. Introducing equation 2 in equation 1 yields the differential form 3 that can be easily integrated to finally obtain this negative exponential curve. So the point Q0 here is the point where the curve corresponding to the falling limb of the hydrograph starts behaving as a decreasing exponential curve. An example is given here. The flood recession curve indeed appears as a straight line in logarithmic axis. So here this vertical axis of the discharge is logarithmic. This line can then be extended until the abscissa of the peak discharge. The line then joins the starting point A of the runoff hydrograph. The part below the blue line is thus the baseflow, and the part above it is the direct runoff hydrograph. With this, we finish this lesson. See you for the next one, where we will see how to construct runoff hydrographs using rainfall data.